Hello, and welcome to this part where you will get some questions and answers related to the content of lectures 1 and 2. The first question is quite simple. So what is the difference between classification and regression? There is just one correct answer and it will be displayed after the timer ends. The correct answer was D. So in regression, the output, or what we want to predict, consists of continuous values. But in classification, the output consists of classes like A, B, C. These are just categories. Now, given this description here, what kind of machine learning methods will you use? The correct answer is C, clustering. And the reason for this is because those news articles are unclassified or unlabeled. So we want to find groups in an unsupervised way, such that the articles within the same group are more similar. And we don't know those groups beforehand. We just want to group the news articles into different clusters. So this process is called clustering. Given two arrays A and B, which of the following results in an error? There is just one correct answer. The correct answer is B, so this one. So this will give you an error. And what we are doing here is multiplying the matrix A and B. So this is matrix multiplication. And this is only possible to do if the number of columns in the first matrix is equal to the number of rows in the second matrix. But if we take the array A, it has shape 2, 3, so 2 rows and 3 columns. And B also has the same shape. It has 2 rows and 3 columns. So we cannot directly multiply the matrices A and B because the number of columns in the first matrix is 3, but the number of rows in the second matrix is 2. Okay, and if you write A times B like in here, then this is the element-wise multiplication. So each element of A will be multiplied by the corresponding element in B. So this will give you a new matrix which has the same shape, 2, 3. And the first element will be 1 times 10. The second one will be 2 times 20, 3 times 30, 4 times 40, and so on. So this is possible. And then here, A transpose multiplied by B, this is also possible. Because when you transpose A, it will have the shape 3, 2. And then multiplied by B, which has shape 2, 3. So this is possible because the number of columns in the first one is equal to the number of rows in the second one. And this will result in a matrix which has shape 3, 3. And this one here is also fine because here we are multiplying the matrix A, which has shape 2, 3. By B transpose, and B transpose will be 3, 2, right? So this is possible because the number of columns in the first matrix is equal to the number of rows in the second matrix. And this multiplication will result in a matrix which has shape 2, 2, right? So only this one results in an error. Now, given a hypothesis function h for regression, read this description here and try to find out which of the following functions is a correct or valid measure of the error of h on the dataset X. There is only one correct answer. The correct answer is A, and this is just the mean squared error. And we can write this as 1 over n, and then here we have the sum over all the data points from 1 to n. And then here we have the difference between the true output for the ith data point and the predicted output. And here we have squared. And this is exactly the same as this one, because we have a vector of outputs, y. So this is a vector from y1 until yn. So that's y. And we have a vector of predicted outputs. So this is y hat. So we have n predicted outputs. And this difference between the two vectors will be a vector of n values, of n differences. And so what we are doing here is to compute the dot product between this vector difference and itself. And this dot product is exactly this part here. So this is just the sum of the squared errors. So this whole thing here, the mean squared error, can be written in this way. Now please read this description and choose the one correct answer among those. The correct answer is A. You have seen this during the very first Python lab. So by putting the parameters of each model as a column in this matrix, then you can predict by doing just the multiplication of the data input data X with this matrix, and then you'll get the predictions based on all three models. You can check Lecture 1 Basics and Lab 1 for more details about this. Now, suppose that you want to solve a linear regression problem by minimizing the sum of the squared errors, right? So this is your cost function. And for example, let's say that you do that using gradient descent. So what is the correct answer among those? The correct answer is B. So we get just one global minimum. Because as you saw in the lectures and labs, the sum of the squared errors is a convex function. So it has just one global minimum. Suppose that in Python you are given a two-dimensional array A and a one-dimensional array V. So this one has shape 2 by 3 and this one has shape 3. So 2 rows, 3 columns here, and this one has just shape 3. It's just a rank 1 array. It's not considered as a column or as a row. It's just an array of 3 elements. And so the question here is, what will be the shape of the result in each of the following cases? So for each of those, specify what is the shape of the result. And also, if one of those leads to some error, then just specify this. For the first one, we have v plus 10. So this will just add 10 to each element in v. And what happens internally here is that Python will understand that you actually want to add v with this array of 3 tens. This operation is called broadcasting. And so you will get, as a result, when you add v and this, you will get a vector which has this shape, right? So an array which contains 16, 15, 12, right? So it's just a rank 1 array of 3 values. Now here we want to add a and v. So we have a plus v. Normally you cannot add two matrices if they don't have the same number of rows and columns. But here Python will do an automatic broadcasting again because it will understand that you want to add v to each row in A. So it will broadcast v so that it has the same number of rows as A. And then just compute the element-wise addition between them. So the result will be a two-dimensional array of this shape, 2 rows and 3 columns. The same thing happens here, right? So you want A times V. So an automatic broadcasting will happen, and therefore you can multiply A and V. So an element-wise multiplication will happen, and what you will get is just a two-dimensional array which has 2 rows and 3 columns, right? So it contains 1 times 6, and then second element 2 times 5, and then 3 times 2, 4 times 6, and so on. Now here we want to do this dot product, or a multiplication of the matrix A and the vector V. So here A has this shape, 2 rows and 3 columns, and V has this shape, 3. So it's not considered as a row or as a vector, it's just a rank 1 array which has 3 values, right? But since you want to multiply A and V, the number of columns in A should correspond to the number of rows in V. So Python will automatically consider V as just a column vector, so it has 3 rows, so that this multiplication A with V makes sense. Okay, and so you will get an array of 2 values, right? So the dot product between this and this will be computed, so that's the first value, and then the dot product between this and this, that's the second value. So the result in this case will be just a rank 1 array of 2 values. Here we want to do the same kind of multiplication, but first we are reshaping the vector V, or the array V, so that it becomes a matrix or a two-dimensional array with 3 rows and 1 column. So after doing this, v.reshape 3, 1, you will get an array which looks like this. So it has 6, 5, and 2. So 3 rows and just 1 column. So that's a 3 by 1 array, right? So now it can be multiplied with A because A is a 2 by 3 array. So you multiply a 2 by 3 array with a 3 by 1 array corresponding to this one. And so this will result in an array which has shape 2, 1, right? Now for the last one, we want to multiply V with A. So we want to multiply V with A. And V has shape 3, right? And A has shape 2 by 3, right? 2 rows and 3 columns. Now this doesn't work even if you consider V as a row vector. So if you consider it as a 3 by 1 matrix, this doesn't make sense. It cannot be multiplied by A because here you have 3 and here you have 2, right? And also, if you consider it as a vector column or as a column vector, So if it has this shape, then also this multiplication doesn't make sense, because here you have one column and here you have two rows. So this multiplication cannot be done. So there is a mismatch of dimensions here. So you will get an error in this case. You have a cost function that you want to minimize. What is the gradient descent update rule to do that? The correct answer is C, so this one. This one is not correct because you have a plus here instead of minus. Now, which one of the following statements is false? The answer is D, so that's a false statement. Because as we approach the minimum of a convex cost function, gradient descent will automatically take smaller and smaller steps. Because as you get closer to the minimum, the derivative gets closer to zero, and so gradient descent will take smaller steps. Which function among those is minimized by an ordinary linear regression, the one that you saw in some previous lecture? The answer is B, and this one corresponds to the mean squared error cost. So this part, x times theta, corresponds to the predictions, because we have d plus 1 parameters, right? and X has shape or dimensions n by d plus 1. So the result of this is a vector of predictions. So you have n predictions. So that's just a vector containing the prediction for each data point. Because if you take this one, this prediction is just theta transpose x1. So this cost here can be written in another way. So you have 1 over n or 2n. The sum over all the data points of theta transpose x or x transpose theta or xi minus yi. This is the true prediction or the true output, and the whole thing squared. So this part here is the predicted output. And so that's the mean squared error cost that you saw in the lecture, and it can be written in this way. Now read this and select the one correct answer among those. The correct answer is A. So yes, we can find the optimal parameters theta for an ordinary linear regression which minimizes the mean squared error cost without using gradient descent. We just use the normal equation. So you can just compute the derivative of this cost function with respect to each parameter theta or theta j, and then set this derivative equal to 0 and solve for theta. Because we know that the derivative is equal to 0 at the minimum of this function. What's the right Python implementation of the gradient update step among those? The correct answer is A. You have seen this before. Now read this description and see among the following conclusions which one seems more plausible or more correct. The correct answer is A. So this was an effective choice of the learning rate alpha because the cost decreases very quickly after a few iterations and then it levels off. So it seems that we are converging. Read this description and select the one correct answer. And the answer is A. We can directly find the best or the optimal parameters theta for an ordinary linear regression problem which optimizes the sum of the squared error function without using gradient descent. So we can just use the normal equation. Read the following description and select the correct answer here using the k-nearest neighbors with k equals 1. And the correct answer is C, because you are given a house which has size of 90, and the nearest neighbor or the closest size is this house which has 80. And the number of rooms of this house is 2, so we predict 2 for this one also. Now select the correct statement among those regarding the k-nearest neighbors algorithm. The correct answer is B. So smaller values of k lead to a more complex model. For example, when k is equal to 1, then you are using just the nearest neighbor to make the prediction. So maybe there will be a large variability among predictions. So such a more complex model, such a very complex model can lead to overfitting. And when you choose k to be very large, then this will lead to a simpler model, right? For example, suppose that you set k equal to n, and n is the size of your data set. In this case, this will lead to a very simple model because you will always predict the same output regardless of the input, and the output will be just the average output over your whole data set. So that can lead to underfitting. Now read this description and select the correct answer among those. The correct answer is C. So a too small value for sigma, which is used here in this Gaussian kernel. So a too small value for this can lead to overfitting because it leads to a more complex model. And a too large value for sigma may lead to underfitting because this will lead to a wider Gaussian, and this can lead to underfitting because this is a much simpler model. So it basically has the same effect as k in the k nearest neighbors, or similar effect to k. And you have seen this in the labs, but in the labs we used gamma instead of sigma, and gamma was defined as the inverse of sigma. It was 1 over sigma squared. And in this case, this kernel function was defined in this way. So using gamma instead of sigma. So in the labs, you had gamma, which had the inverse role of sigma.